Dr. Haidang Nguyen from the University of Alabama. He's going to give a talk on stochastic Kolmogorov systems from a dynamical system point of view. So, Dr. Nguyen.
Thank you very much for the introduction and for the invitation of Dr. Hua Ding. And so today I'm talking about some results. I want to look at the stochastic Kolmogorov system from a dynamical system point of view. So the main results based on some work with Alex Henning, my friend from Texas A&M. And Sebastian Schreiber, he is more senior from UC Davis. So let me get started. This is the outline of my talk. I first introduce about stochastic Kolmogorov systems and talk about conditions for persistence and extinction of stochastic Kolmogorov system, how the idea how we treat this system. And then we talk about some applications, especially when we want to classify two-dimensional and three-dimensional systems. And then I will conclude by some remarks. The thing is that real populations do not involve in isolation, and as much of ecology is concerning with understanding the characteristics that allow two or actually more species to coexist, or one species will be dominant and take over the habitat of another one. And traditionally, the dynamics of an ecological system is modeled by a system of ordinary differential equation. But because the environment is always fluctuating, so when you take into account the effects of the environment, the dynamics of the population inherently becomes stochastic. And when we look at a stochastic model, the combined effects of biotic interactions and environmental fluctuations are very important to determine the growth of the species. And there are some interesting situations that have been discovered, like sometimes biotic effects only can result in the extinction of some species. However, if you add some effects of a random environment, extinction may be reversed to coexistence. And the opposite way can also happen in some cases. The deterministic system exhibit coexistence of two or more species, but then if you have some environment populations, some the species may go extinct. Now let me begin with a simple one-dimensional system. So this one model the growth of only one species. So the well-known logistic equation is given by this one. So R is the growth rate and K is the intrinsic competition rate, to make sure that the population do not explode, right, to infinity. And if you add a stochastic term and a simple term, so a linear term like this, then for this system, the factor to determine the behavior of the system is called stochastic growth rate, which is R minus sigma squared over 2. And it can be shown that when this growth rate, stochastic growth rate, is negative, then the population goes extinct almost surely. And when it's positive, the population is persistent, and the transition probability converges to the unique invariant measure on the positive part, 0, infinity. And and for this simple system, we can even determine the behavior when the growth rate equals 0. In this case, the process is non-recurrent, and in the sense that actually it doesn't go to 0. The sample path doesn't go to 0, but in average, even in time average expectation, the population goes to 0. But we care about the dynamics of an interacting population, and traditionally is when we do not take into account the fluctuation of the environment. Uh, the the model for an interacting population usually given by the equation 1.3 here. So we have term SI, FI here, so indicates that the per capita growth rate of SI is a function FI of of us, the whole population and species. And this system is often called the Kolmogorov system. And now we want to add some stochastic effects. There are many kind of noise, random noise we can add to, but here the most common noise we can use is the noise driven by Brownian motions. And suppose we have the term SIGI times EI, and the vector E here is a correlated Brownian motion. And we want to answer some fundamental questions like under what conditions is the system persistent? Or in other words, under what conditions do n species coexist? And if the system is not persistent, we want to see which species persist, which one go extinct. And well, there are, in the past maybe 2 decades, there may be like a few thousands of people have attempted to answer this question, and even for like some very specific models. But nearly all of them cannot give sharp conditions because they use a common approach, which is like they propose a function and impose some conditions such that the function has some Lyapunov type properties. But the problem with this approach is that the result depends on the choice of the Lyapunov function, which is usually subjective. So because of that, the results are usually very limited, and because the Lyapunov function doesn't reflect the true nature of the dynamical system. But there's also some another approach that basically initiated by like some people like Sebastian Schreiber and Bernay from Switzerland. So they can give some sharp conditions for persistent, but they focus on the compact spaces. And now there are some. What we want to do is that we want to give sharp conditions for persistent in a non-compact space, and also we want to give sharp conditions for extinction too. Okay, so let me define the space. The space we work on is Rn plus 1, which is a set of n-dimensional vectors, n-dimensional non-negative vectors, and the Rn circle plus is the interior, which is the set of positive numbers in n-dimensional. And because it doesn't make sense to work with a negative number for when we study an ecological system, right? And the system we work on is this one, as I mentioned before. So there's some standing assumptions. Assumption 2.1 here. The first one is the functions are locally Lipschitz, and the second one is there exists some condition. Basically, condition 2 is given such that the system has certain kind of boundedness, and usually conditions 1 and 2 are satisfied for almost all of the well-known Kolmogorov systems. And condition 3 is that we assume that the Brownian, the diffusion is non-degenerate. So this matrix is a positive infinite matrix, and then it's easier to work with non-degenerate diffusion. Otherwise, we need to take care of a few more steps, and that is what I will comment later if I have some time. Okay, and then the definition. The species Si is set to stochastically persist if for any epsilon greater than 0, you can find delta such that eventually the probability that Si t greater than delta is greater than 1 minus epsilon. And the system is set to stochastically persistent if all of the species persist stochastically. Okay? And, we can, for the initial data little x, we set that the population Si goes extinct with probability p sub x, which depends on little x. If the probability that Si goes to 0 is little p of x, and when little px is 1, we say that Si goes extinct almost surely. And the probability, the measure pi is an invariant probability measure of x when we start the process with initial distribution pi, then the distribution of st continues to be pi for all time t. And the set of invariant probability measure is convex, and the extreme points of this set is called ergodic measure. So in other words, any invariant probability measure can be represented as a convex combination of measures. So what is the main idea of our approach? So if you look at a deterministic setting, when you want to characterize the asymptotic behavior of a system, you can look at around an equilibrium. You can look at the Lyapunov exponents of the linearized system around that equilibrium, right? And if all of the Lyapunov exponents are negative, then this is stable. Otherwise, if you can find a positive Lyapunov exponent, the equilibrium is unstable. So here we want to do a similar thing in a stochastic setting. We look at the behavior of the system near the boundary to determine whether or not the system is persistent. So for instance, this is the equation of the equation for the long-term growth rate of st. Suppose t, little t is sufficiently large. Then you can see that when t is large, the growth rate of log it divided by t is given by this one. And the first term here on the right hand side and the second term can basically small when t is small, when t is large. So we only focus on the red term. And if x is close to the support of an ergodic measure mu for a long time, then the red term can be approximated by the average with respect to the measure mu of this function, of function fi minus gi squared times sigma I divided by 2. And we denote this one by lambda I of mu. So because the first and the second term are negligible. So lambda I mu defined by this one, we determine whether xi goes to 0 or xi does not go to 0 when x is close to the support of mu, and lambda I mu is the ith Lyapunov exponents of mu. And so that is the idea of how we define the Lyapunov exponents for a stochastic Kolmogorov system. And let M is the set of ergodic probability measures of S supported on the boundary. And then for each ergodic measure, because the diffusion is not degenerate, so the support of an ergodic measure must be a subspace of Rn plus. So basically, it means that there are some index, some components, some index like I mu here are the index at which the components are positive, and E mu is the set of indexes where the components are equal 0, and that is the subspace. And for I little I belong to capital I mu, we call lambda I mu internal Lyapunov exponents, and for the other one, when I is in E mu, we call lambda I mu external Lyapunov exponents. And the fact is that all of the internal Lyapunov exponents are 0. It's expected because you can imagine that if the species involves according to the ergodic measure mu, then the process does not tend to go decay to 0 or grow to infinity in that support. And because of that, the internal Lyapunov exponents must be 0, because if it's positive, then that species goes to infinity when it involves according to mu, and which is not possible. And the same thing happens if lambda mu smaller than 0, because it will show it will lead to a contradiction that some species goes to 0. Okay, so because of that, we only care about external Lyapunov exponents, and an external Lyapunov exponent is often called invasion rate. Sorry, battery. By biologists, because if you have imagine that if you have a sub population including the species N1 and K, and then you introduce another species I, for I belong to the set E mu here, then if you introduced the species I with a small initial density, then lambda I mu, if lambda I mu smaller than 0, species I tends to decrease. So kind of species I cannot invade into the sub community indexed by I mu. And when it is positive, then the species tends to increase. So it means that species I can survive in this case. So the invasion rate is positive. And this picture can represent something like this. For instance, species the invariant mu 1, 2 here in this case lies in the subspace generated by OS1 and OS2. So lambda 1 and lambda 2 of mu 1, 2 must be 0 because they are internal Lyapunov exponents, and the the value lambda 3 of mu 1, 2 is the external Lyapunov exponent. And for instance, if you look at mu 1, which lies in the axis OX1, then lambda 1 of mu 1 is the internal Lyapunov exponent, and lambda 2 and lambda 3 of mu 1 are external Lyapunov exponents. And so the idea of the main result would be very simple from a dynamical system point of view. The idea is that if all of the invariant probability measures on the boundary are repellers, then the system must be persistent, because whenever it is close to the boundary for a long time, then it could be pushed back to the interior because of the repellers on the boundary. And otherwise, if there exists an ergodic measure on the boundary, which is an attractor, then extinction can happen, because when the solution is close to the attracting domain of the attractor, then attraction will happen. It can be attracted to the boundary, right, to the support of the attractor. And because of the diffusion is non-degenerate, so there are only two possibilities that whether the solution tends to boundary with probability 1 or the solution does not tend to boundary with probability 1. So because of the degeneracy of the diffusion, we can narrow down only two possibilities, and they make us pretty easy to make the system pretty easy to handle. So this is the consistent for the condition for persistent. So the condition for persistent is that all of the invariant measures are repellers. So what does it mean by that? So how can we define a repeller? So it's simple. The repeller means it means that the maximum Lyapunov exponent is positive, right? So if this one is satisfied for all of the invariant measures, then S is stochastically persistent. And we can also show an important technical result that the transition probability converges exponentially fast to the invariant measure. And this is very important, especially when we want to run a numerical simulation to find the to estimate the to approximate the process ST. And in the biological point of view, this exponential convergence can be considered as some sort of resilience of the species. So despite some changes of the species, we converge, we come back to the statistical statistical equilibrium, which is the invariant measure, pretty fast. And what is the condition for extinction? Is it just the existence of an repeller, of an attractor? So the main so what is an attractor? An attractor means that the maximum external Lyapunov exponent is negative, because we know that the internal Lyapunov exponents are zero, so we exclude them. And the condition is the maximum likelihood exponent is negative. And the condition 2.5 here is a little bit technical, but it means that the attractor is a sink, so some kind of robustness in its own space R mu circle plus. Okay. But this condition is not restricted, because usually that is a condition for the for the existence of the attractor mu. Okay, so now we know that under condition 2.4 and 2.5, the system is not persistent. But we want to go further. We want to we want to know which, we want to characterize which species go extinct, which one persist, and the assumption we need one more assumption. So basically, this assumption means that we want to exclude the cases that we do not know whether they are attractor or repellers. We don't know whether they are attractor or repellers if the maximum likelihood, maximum external Lyapunov exponent is zero, right? Even for a deterministic setting, when you look at an equilibrium, when the maximum Lyapunov exponent is zero, you cannot say anything about whether the equilibrium is stable or not. And we, assumption 2.2 is that we don't look at these cases. And if we look at exclude these cases, we can show that okay, the probability that the solution converges to the boundary is 1. And basically, this condition means that if you have assume that you have 3. Suppose you have 3 attractors, then the solution will converge to each attractor with a positive probability, and the probability and the sum of probability is 1. So always it must converge to one and only one of the attractor. And when it's converged to an attractor mu, then we know that all of the species that doesn't support by mu go extinct with the exponential rate of nothing but the Lyapunov exponent of mu lambda I of mu. So that's the main result, and now I want to use the main result to classify a two-dimensional system. This is a two-dimensional system, and the first equilibrium on the boundary you can think of is when x is 0, y is 0. So you have a Dirac measure at the origin, and the exponents, Lyapunov exponents, are given by lambda I of delta is this value. This is straightforward. And so when you applied the main result to the one-dimensional space, which is the two axes of this two-dimensional system, we can show that lambda I delta is, if lambda 1 delta is smaller than 0, there is no invariant measure on the horizontal axis. And if it's greater than 0, there's an invariant measure on the positive part of the horizontal axis. And we have the same result for the vertical axis. So delta mu1 and mu2, if they exist, are ergodic measures, and you know, for this one-dimensional, you can define density of mu1, mu2 by solving Fokker-Planck equations, so that you can have a formula for the Lyapunov exponents with respect to mu1, mu2 that are given in terms of some integrals. So I will go through some cases, all of the cases except for, like I said, critical cases when the maximum external Lyapunov exponent equals 0. We cannot do anything about that, but actually there's something we can do, but it's not the main purpose of this talk, so I will exclude these cases. And if you exclude these cases, here is the classification. This is the first case when 2 Lyapunov exponent at 0 is negative. So this is the only invariant measure, and it's an attractor, so all solutions will converge to this part, and x and y go extinct. And now I assume that let's look at the right-hand side, the picture on the right-hand side, because the left-hand side is just when you swap x and y. So for the right-hand side, lambda 1 is negative, so and lambda 2 at delta is positive. So there is no mu1, but there exists mu2. And suppose that lambda 1 of mu2 is negative, then This one is an attractor, mu2 is an attractor. So the solution will be the only attractor, and solution will converge to this attractor. So X go extinct and Y persist. On the next case, suppose that there exists mu2 but not mu1, but lambda 1 of mu2 is positive. In this case, two ergodic measures here are repellers, so X and Y coexist. Okay, and this is the case when at delta, at the origin, both Lyapunov exponents are positive. So there exists mu1 and mu2. And suppose one Lyapunov exponent of mu1, so Lyapunov exponent of mu1 is positive, and Lyapunov exponent of mu2 is negative. Then this one is the only attractor, and X goes extinct and Y persists. And this is the case when all of the Lyapunov exponents are positive. So clearly that all of them are repellers, and X and Y coexist. And this is the case when mu1 and mu2 are both attractors. So when they are both attractors, we know that X and Y do not coexist, and both go extinct with a positive probability depending on the sample path converge to mu1 or mu2. Okay. And then you can whether it's converged to the vertical axis or the horizontal axis. We know the other species will goes to zero at the rate lambda 1 of mu2 or lambda 2 of mu1. Okay, so let's talk about higher dimensional system. So the result I presented before works very well for two-dimensional, and it still works pretty well for higher dimensional systems, but there's still a gap between the conditions for extinction and persistence. What is the gap? The gap is for persistence, we require that all invariant property measures on the boundary are repellers. For extinction, we require that an ergodic invariant probability measure is repeller. So the gap here is that one is required for all invariant measure. For extinction, we need that invariant measure to be ergodic. And this gap can be seen when we try to classify a three-dimensional system. The question is, how can we close this gap? The idea is that if you have in a deterministic setting, if you can there is a concept of Morse decomposition that's given us like a directed graph about the invariant measures of the dynamical system, like the graph, the directed graph, this tells us about like when the solution is close to one invariant measure, it will go to somewhere, which invariant measure, and so basically it tells it's a roadmap about the behaviors of the flow. And if we are able to define a Morse decomposition for a stochastic system and obtain needed properties, then we can close that gap. And suppose that we were able to have a Morse decomposition for, and then the condition for persistence could be like suppose this is a Morse decomposition. Then the condition is that we need the maximum Lyapunov exponent in each of the each subset of the Morse decomposition to be greater than zero, and then the system is persistent. But so far there are quite a lot of technical difficulties in how we can define a Morse decomposition for a general stochastic system. So we have not been able to define it, but the thing is that if you are given a specific model when we examine that, we know how a mass decomposition looks like, even that we don't have a rigorous definition for that, and that enables us to determine the asymptotic behaviors. And in the our recent work, we classify the asymptotic behaviors for a stochastic three-dimensional system using this idea. And there is something nice about stochastic system is that the classification is still incomplete for deterministic system, but for non-degenerate stochastic system, our classification is pretty good. Like it's only exclude critical cases when the maximum likelihood is the maximum Lyapunov exponent is 0. So we have totally 9 cases up to permutation where at least one species persists. For instance, this one only one X1 persists, and this one means that only one species persists. So, 3 cases in the first line here. In 3 cases in the first line here, only one species persists. This one, that species is S1. This one, the species can be S1 or S2. And this one, the species can be S1, S2, or S3, but only one of them persists. And the second line, the second row here, contains 3 cases where exactly 2 species persist, but we don't know. For instance, in this one, we know the 2 species are S1, S2. Here, the 2 species can be S1, S2, or S1, this one is different. This one is S1, S2 can persist, or S3 persist. And this is the case when S1, S3 persist, and or S1, S3 persist. And we have a few more cases. Here is the only case when 3 of them persist. So the idea is that 7 cases can be handled by the results presented in the first part of my talk. So 7 cases can be handled without using the idea of mass decomposition. Use the theorem 2.1 and 2.2 I presented before. And 2 cases need to use the idea of mass decomposition. The first one is like a rock paper scissors system, right? When A beats B, B beats C, but C can beat A, so it becomes a cycle like this, a cycle like this. And in this case, you cannot cheat. For instance, the system we work on for three-dimensional system. The system we work on is that, let me see. This is actually this image. So that case. So basically, we suppose that there exists mu1, mu2, mu3 in the positive parts of 3 axes, but there are no ergodic measure on any surface, because if we exclude species 3, species 2 would beat species 1, something like this. So if we remove one species will prevail and the other one will go extinct. And in this case, you cannot treat mu1, mu2, mu3 separately. It forms a cycle, so you need to treat them as a subset of 3 invariant measures. And the graph is like this. From delta, it can go to mu1, mu2, mu3, and between mu1, mu3, and 2, mu3, it has this cycle. And then using that, we have the following theorem. Basically, if all the product of positive Lyapunov exponent is greater than the product of negative Lyapunov exponent, like this, then three species we persist, coexist. Otherwise, if this condition is satisfied, if this one is negative, then the solution will converge to the boundary. This is the case when the solution converges to the boundary. It can be between mu1, mu2, and mu3. Okay. So that is one case. And the other case that we cannot use theorem 2.1, 2.3 I presented earlier is when two competing preys sharing a predator, and assume that if without the predator, there would be exclusion between two preys. So they competing, they compete aggressively. So at least exactly, so the one of them will go extinct without the predator, but the predator can serve as something like a biological control. So they make the competition of prey less aggressive, and then three species can persist. And in this case, the direct graph is something like this. And using this direct graph, you can construct a Lyapunov exponent to show that here we do not have circle. So like we do not have from mu2 1, it cannot come back to mu2, or it cannot come back to delta, something like this. So we do not have a cycle here. And after and using that idea, we can construct a Lyapunov function to show that there are no circle, and using that we can we can obtain the result, which is if all of the Lyapunov, if all of the organic methods here are repellers, then the species, all of the three species coexist. And if one of them is negative, means that one of the two here is unattracted, then coexist, then extinction happens. So that is two cases that you need to use the Morse decomposition idea to handle. Let me finish by some remarks. So recently, we are able to relax. This is a preprint with my friend Nguyen from University of Connecticut. He is looking for jobs now, and he's very good. So the rate of convergence, we can relax the condition about the boundedness that this one. Let me show again. This condition. Condition 2 here. And we can relax some condition for boundedness and the rate of convergence. Now, after you relax that condition, we do not get the exponential convergence anymore, but we can show that the rate of convergence is polynomial under some milder condition. And our methods here we treat generate heterogeneous. We treat homogeneous population models, but our methods can pave the way to treat heterogeneous population models. And a way to model spatial heterogeneity is to consider a population living in an environment consisting of n distinct patches, and there is dispersal between patches. So in one of one paper about 5 years ago, I consider one species living in ant patches, but we can also work with ant interacting species living in ant patches. Okay, and we also generalized the results to a stochastic Kolmogorov system with delays when we take into account the delays effect, and which is unavoidable in a ecological system, because clearly that the dynamics of species depends on a few things in the past, like because of something like such as the time of hatching, something like this. And when we, of course, when we work with a stochastic Kolmogorov system with delays, it becomes a macro process in an infinite dimension, infinite dimensionally system, and there are lots of technical issues there. And our initial papers, not a papers, but a couple of papers treated stochastic Kolmogorov system with biotic delays, and in the long run you can also work with infinite delays. Okay, and I think that's my talk. I will stop here. Thank you very much.
Yeah, thank you very much. An interesting talk. Do you have any questions for our speaker? I have a quick question, Dan. You mentioned in the last slide that you work with infinite dimensional spaces and cases, but actually reality is discrete and finite dimensional. So, uh, what's the purpose of move from finite dimensional to infinite, and then you go back to finite dimensional for application?
No, the thing is that if you look at a system of like this, this is a stochastic system without delay. So with this system, the process st is a macro process. And now if you assume that the function f here, fi here depends on not only st here, but also depend on some segment of history, then the system, the process st is not a macro process. So there are a lot of macro properties that cannot be applied here. In order to define a macro process, you need to look at not only the value of the process at t, but the value of the process at an interval like from t minus r to t, where r is the delay time. And then that process is a function valued process, and a function valued process. That function value process is a macro process, but here the space, the samples, the space now of that process, the state space of that process is the set of functions which is infinite dimensional.
Okay. All right, thank you. Do you have anything else for our speaker? So if not, let's thank our speaker again for his interesting talk, and we see you next week.
Okay, thank you. Thank you for the invitation.
Thank you everyone for being here today.
Okay.